All right. Charge carriers and semiconductors. So electrons are filling valence band at 0 degree Kelvin. Now, for them to become available for conductivity, two conditions needs to be met. They have to jump from valence band to conduction band, and in conduction band, they're supposed to be free energy sites for those electrons to occupy, so they can then get swept away under the applied bias. So let's go through the steps. When the few definitions also, when electron jumps from conduction band, jumps to conduction band from valence band, we say that there has been electron hole pair formation. So we use this word EHP. Whenever you read EHP, that should tell you this is nothing but idea that an electron has jumped, and for whatever reason, it may be uh, optically excited, it may be heat, it may be external energy, it may be mechanical. So, and whenever that happens, it leaves behind a hole. So, when there is a hole left behind, a pair has been created, and that pair is what will then be involved in the charge transport current. Now, the most common source of that process is heat energy. So at 0 degree Kelvin, just a small animation, everything is full. And as you crank up the temperature, they start jumping up. And now more and more electrons become available, right? So you keep on cranking the temperature. It's going to take forever, 10, 11, 15. I'm going to just jump through a lot of that. And what you get is after a while, they all should go there. Why is not doing that? So yeah, the animation runs up to 300 Kelvin. So by that time, you have many electrons available in the conduction band. But then one can say, okay, if there are so many electrons available, why don't we just use them as is in our devices? Even though there are many electrons, but we want a continuous supply. We cannot depend on temperature. You cannot depend on your device to work if temperature is suitable. So we don't base the conductivity or charge on the only on heat. So we want a mechanism that as soon as you turn it on, they should be available, and that happens by impurity, by introducing materials from outside world, because those impurities will do a couple of things. They would add energy levels within the band gap, and they would introduce many more charge carriers to the material. Once you do that, you can then control the conductivity of semiconductor with very precise amount of impurities. So we know exactly how much impurity will result in how much of conductivity, right? So we know then how much would be available there. But without that, we have, even without putting those impurities, we know there is some what you call uh, intrinsic amount of charge, intrinsic amount of charge carriers available because of heat. For silicon, uh, we know the number that's 10, what? We take it 1.5 times 10 raised to power 10. Sometimes just use 10 raised to power 10, but to be very precise is 1.5 times 10 raised to power 10 number per centimeter cube. That's how we count how many are there. And this is coming from the atomic density of, silicon, which is 5 times 10 raised to power 22 number of atoms in there. So think about it. We have 10 raised to power 22 and you just get 10 raised to power 10 to the order of 10 raised to power 10 intrinsic charge carrier, very few. So that means there are many empty states in valence band and many occupied state, but not enough. Number one. Number two, they totally depend on outside energy for that EHP formation to happen. So we cannot keep track or we cannot exactly use these numbers. So we have to add outside charge carriers. Now, without doing any, we'll get to doping, we'll get to how we introduce external charge carriers, but just in a simple device, simple uh, semiconductor material, if you think about movement of charge. So suppose we make one electron jump into valence band. So when that happens, it can create a hole at the back. So that hole or empty side, an electron can move and occupy it. And there's now another hole formed. Next electron can occupy that one. So they can keep on doing. So what we can see from the outside world is that electrons are going right one at a time and holes are going left. So, but if that electron jumps back with temperature, it's just a random process. It can stop that conductivity. So at the end of the day, there will be no net current in the band unless that electron is completely removed, right? So that's the overall thing, that for conductivity to happen, it has to completely go out of the system. Only then it can do that. Now, when we are making these devices, we have conduction band and we have valence bands, we often apply voltage across. So when you apply voltage, the effect of voltage on the band diagram is we show the band to be bent. We show those energy bands to be bent. So that's a way of showing that if an electron is on the higher side, that's higher energy level. It has to come down, move to the lower energy level. So here is an example given that if there is an electron which is located at this position, it's high energy, so it will travel and try to come at lower energy level, because up, as I told you before, is higher in energy for conduction band, lower is higher for energy for valence band. So here also, holes would want to come down lower and lower to lower energy levels. So for both sides, their references are higher energy on that side, this is higher energy on that side. And this would be the effect of applying a voltage across a semiconductor material.